Thank you very much. So a little bit of background. So I was, when I submitted the title, I was going to tell you that we should really look for getting rid of all those kernel programming languages and low-level, like assembly-like or domain-specific low-level languages. And I don't have to tell you anything about domain-specific architectures and languages and frameworks after Saman's and Maya's presentations. I think this is pretty clear. That's what everybody wants these days. But I was really pissed off that more and more people end up writing low-level code for these domain-specific accelerators, while we could have hoped that domain-specific frameworks and languages and high-level specification would have solved the problem for a long time. Now, when preparing the presentation, I realized actually it's not that simple, and maybe we have to live with kernels a little bit longer. Oh, sorry.
Just right there.
Oh, okay.
Yeah.
Oh, like this?
Yeah.
Do I look nice?
Yeah.
All right. So I'm not going to sing any K-pop anyway. So yeah, I mean, normally we should have solved that problem already. And actually, I give you some examples where some areas where we reasonably solved that problem, and some people called it performance portability. And yes, it's a dream for a long time. As I was saying, kernel programming is back, so maybe we have to live with kernels, and basically that's what I figured out in the last few weeks when preparing the talk. So maybe we should stop worrying instead. So maybe we should come up with frameworks that are both domain-specific and can live with performance engineers or some corner cases, or maybe even more than that, where actually we do have to program low-level stuff, and maybe have the two worlds coincide. So with the culprits, why do people actually write kernel code, low-level code? So in the field of AI, and at Google in particular, of course, Gemini is the culprit. So like generative AI, and when you want to write code for a variety of devices, for a variety of models, shapes, and sizes, and different frameworks from TPUs, like embedded TPUs, to CPUs, GPUs, etc. So people end up writing low-level code all the time because we just don't have time. People want to have the next generation Gen AI product on the market yesterday. And the best way to get things done fast is to just forget about nice infrastructures and abstractions. At least in the short term, that seems to pay off. But that's not something we like. And as systems people, we know this is a dead end, but still, history repeats. So yeah, I'm not going to tell you, I mean, you know about low-level programming languages. Triton was mentioned in the JAX world. It's called Pallas. It's actually much better than Python, but Triton. It's embedded and it's differentiable, and it has all kinds of composability features. Outside of the GPU world and CPU world, you have a lot of need for low-level languages as well. Every time you design like a memory accelerator or any kind of domain-specific hardware, you need typically a low-level framework that goes with it. So it's not only performance that matters, it's also expressiveness limitations. People write low-level code just because the high-level abstractions sometimes don't work. So unless you work at MIT and you know how to design stuff with build it, or unless we actually would adopt build it, people end up just, they don't know how to do it. Or it takes too much time, so they don't even think of building a high-level flow, and instead they go straight to a low-level flow, although some of the techniques remain common. So actually there has been success. And when I joined Google like 5 years ago, XLA was essentially doing the job for AI acceleration and models. So you start from a high-level domain-specific compute graph, which happens to be static data flow graph. Every information is essentially statically known, even like tensor shapes and everything, and sizes. And this forms a nice domain-specific abstraction for both inputs, like ML frameworks, and optimizations, like analysis and graph-level optimizations and low-level code generation, etc. So that kind of worked. It actually embeds internally a just-in-time compiler that can do all kinds of even rematerialization tricks, fusion, tiling, vectorization, all kinds of things you need for addressing real architectures. And memory management in particular is completely abstracted away. So like high-level frameworks only think about tensors, but not actually about buffers and arrays. So that's great. And we know it has been successful in other areas as well. And we even went into some more like old school automatic parallelization work, saying, since we have these domain-specific frameworks, can't we also leverage those frameworks for analyzing existing code, legacy code, or maybe write low-level code and hope that we can also raise the level of abstraction. So that was with folks from ETH Zurich, among others. So they like skiing, etc. So we have this abstraction of going down the slope is the nice way, domain-specific way of getting performance. But somehow you need a lift also to get you up there. Otherwise, it's just too cumbersome, unless you're into alpine stuff. And we had actually pretty good success leveraging MLIR and other like modern software engineering techniques to make this lifting reasonably deterministic. Of course, I mean, that's particularly interesting when you have expressiveness limitations, but you cannot just take arbitrary dusty DAC codes. Of course, this still remains a hard problem. Yes, so this is a nice picture. I told you about lifts. Some of you may have seen that picture before because I presented it I generated that thing for a keynote like earlier this year. If you do like if you ski and if you take lifts, you would rather not take that gondola, particularly because it's actually hanging from the cable through one of the security like protections that make you normally not fall out of the gondola. So I don't think this is really stable. But that's what the version of Gemini at the time was producing when you asked for a gondola. Also, it's going down the slope, which is really cool. But that's really the filter through. If you ask performance engineers how they see compilers and high-level programming languages, that's what they think about. Something that's that's a complete misfit. So they have zero trust in compiler optimizations, in abstractions, actually still coming with a lot of penalty. Expressiveness is limited. Yes, if you fit these nice data flow graphs, you're happy. But if you're not, you're stuck. You have to redesign everything from scratch. So yes, people understand that domain-specific frameworks are a thing, but they don't really trust that those things can cover the full space of their interest. And I think Maya made it very clear in HPC. There are so many algorithms, so many tracks. There's so much experience doing high-level programming in LaTeX and how to actually translate this into like this single line of LaTeX into some efficient distributed code. I mean, people do that all the time, and they never came up with really a single domain-specific abstraction. So we have to live with this. I mean, this is the reality today. So of course, there are nice places where we are comfortable, like matrix product, linear algebra, BLAS, etc. We know how to systematically decompose matrix product, like for example, the BLIS methodology let you tile things for different levels of hierarchy and vectorization, etc. All the way from wafer scale acceleration all the way down to tiny edge accelerators. That's great, but it's not enough. I mean, if we really want to address the needs of our compute-hungry Gen AI systems, you have to look at the T of ChatGPT, for example, to do that, like transformer networks. They are not just matrix products. If you look at this formula from the distance, it looks like there are basically 2 matrix products. Actually, there are 5, because the Q, K, and V matrices are also the results of matrix products. But if you want any locality and any reuse in this formula, you actually have to dig deeper, and you have to fuse, and you have to tile, and you have to do all kinds of usual tricks. And this is not going to come out simply of BLAS. You actually have to transform the full attention layer to get it right. In particular, if you want long context, which is a very big deal these days. For example, Gemini actually just got up to 2 million tokens of context. Since the context length is like the complexity of attention is typically quadratic in the context length, you have to do all kinds of things to make it work. It cannot just be naively scaled. There are many ways. Of course, there are algorithmic ways. There is a lot of model architecture search and ML algorithms research, but also many ways at the system level. And parallelism is one of the solutions at all levels in every possible dimension. So I don't have time to go into any detail here, but any possible lessons in parallel programming you learn is applicable in that field, even for inference alone. And that table on the right is just a story about inference on the TPU v5 chips. For a large enough model, you need actually a full pod or maybe several pods just to run inference. Whether that actually makes sense economically speaking is another story, but that's what you need. And it's not only parallelism, it's also specialization, as we all know here. The reason we need to pay attention to specialization here is that any parallelization techniques alone will not tell you how to offload computations, how to store the data in the right memory space, when to asynchronously transfer things from one domain to the other. All these things have to be taken care of. And the performance cliffs in these decisions, in these specialization decisions, are extremely painful. They are extremely high. So parallelism, sometimes you can get it wrong by a few percent, but the cliffs, if you don't use the right memory, I mean, actually going back and forth, again, your story before, Maya was exactly in that space. So if you have to just use the wrong memory interface or DNA, it completely defeats the purpose of specialization. So that's why people do kernel level programming. I mean, if the framework would do it automatically, it's great, but it's actually quite unlikely, and it may take time to get it right. Another example is code generation. Yes, it's not all about code generation, but at some point, for example, if you want to optimize attention, you have to tile and fuse. And flash attention is like the most popular technique to do that on GPU, but there was a similar technique on TPUs before, even at Google. You have to actually play mathematical tricks as well. So typically, you have to know that exponential of sum is the product of exponentials. You have to renormalize things along the way. So there are some complex math going on. It's not a simple compiler trick. It's a very domain-specific trick you have to implement. And yes, people can do that, but it takes time. Implementing that in a DSL takes months, but again, the clients want it today. So from an industrial perspective, it makes sense. And in the case, even for publishing a paper from those guys at Stanford, it made sense to do it all the way down in CUDA, and it took a few weeks or months before it actually was replicated in Triton, or using MLIR in our case, which was later than the paper was published. So there is rationale for doing low-level kernel stuff. So let me step back a little bit, and maybe that's the main message of the presentation. I don't have anything written there because I don't want it to be quoted for it. But maybe that's the TLDR is that we have to learn kernels, to learn to love kernels somehow, and some of the forces are not technical. I know I'm being recorded, I think, but anyway, I'm going to say it. I mean, one of the reasons people do kernel programming is not just because of expressiveness and because it takes too much time to discuss with compiler folks. You'd rather do it yourself. It's because of personal interest. So if you have to publish a paper, or example before, or if you have your performance evaluation that's coming soon, and there is Gemini asking for help, you'd much better do it like today rather than discuss with another team and beg them to do it in 3 months. So if you can do low-level stuff, you'll do it yourself. And I think that has plagued the industry for quite some time, and we are back at this. It's not, in ML, we had this dream period where XLA and automation was everything, almost everything. It's not enough. I mean, if you have these social and economic aspects as well at play, you get people to actually write low-level code because it's their own interest. Maybe not the long-term interest, but that's their own interest. And that's what people end up doing, unfortunately. Anyway, a few directions. I don't have much time, so I want also to some interactions because I'm mostly asking for help here. And I mentioned that in some earlier presentations as well, but of course, Simon also said everything. So yes, you want reflective programming, you want like meta programming of all kinds of sorts, but it has to be well behaved. Like you want to preserve some form of composability, you want to preserve soundness as well. So embedded DSLs that let you optimize the way in the user schedulable ways, optimize the code in user schedulable ways is great, like Halide, etc. But it has to be more extensible than just one DSL like Halide. Build it is a great case. It's a great example, I think, of the type of frameworks we need for quickly developing DSLs for any purpose. So in our case, we did not use build it, and I will tell you what we did internally for all kinds of reasons. But I think this is still the way to go. Another approach, staging and partial evaluation. So build it uses this all the way through. So a while back, we had this vision of implementing loop transformations like tiling, fusion, etc., using staging. And it ended up being kind of messy, mostly because we didn't have, I think, enough introspection capability. So if you want to do like loop tiling, you have to anticipate that you don't want to lower the loops too early, so that you can still later on decide which loops to permute, which loops to reprocess. So basically, you have to build some kind of AST that lets you build the the few dimensions of computation in an abstract way that will let you decide how to tile eventually. So that's what you're doing with built-in. But if you use pure multi-stage programming, and we wrote a full paper about that, it's not enough. I mean, it's painful. You can do it. You need higher order functions, etc. But it's not really practical. So it was kind of a negative result turned into a paper, but that shows you need more than just macros. You need actual DSLs with abstraction and analysis capabilities. And I'm just repeating what you say. Yeah, it was a few years back. There are other approaches, like any DSL is also just like built-in is a framework, the vision of how to use multi-stage programming for domain-specific framework construction that I like. I'm just advertising for it, but all these reasons are, I think, fundamental reasons why Python is being used. I think people have all kinds of reasons to use Python, but eventually what matters for most high-performance computing projects is this capability to, maybe it's string level, maybe it's untyped, maybe it's very dangerous, etc. But you can still build frameworks that do the job. So there are tons of complementary approaches as well, where ML is everything. Of course, if you want to publish these days, it's great to be ML-based, like ML-enabled compilers, for example. So some students from IIT I worked with recently came up with a list of 200 plus works using ML for compilers. So that's great. So we decided to just write one paper. Basically all these works, they tend to be limited in a single way, which is how compilers open the knobs and what surface you have to interact with the compiler for doing ML-based stuff. So if you're in pure auto-tuning, you typically have flags and a few knobs to like tweak the heuristics. If you want to go beyond that, more ML-enabled heuristics, you actually have to open the compiler internals and decide how to replace some expert written heuristics in C++ or in Python or whatever with ML-based models. But then the problem is, how do you interface state-of-the-art ML models with compiler internals, especially C++ based? And there are many ways to do that. It's mostly software engineering. Depending on whether you want to train, to deploy, to go into production, or to write a paper, there is a big difference. And this paper is just about that, telling you all the ways you can actually do it with more or less overhead and benefits. User scheduling languages, it was discussed at length by Sept, so I don't have to go into this. There was also some work, at the same time we were working on multi-stage programming, we also worked on using pragmas for schedules. And so that was really a hack, using low-level rewrite rules and like syntactic stuff on using pragmas for implementing transformations on top of existing OpenMP code. It was called the X language, together with UIUC and Keshav was still at Kernel at the time, so that's really a long time back. And we did actually we had pretty good success, but with zero guarantees. So that was too low-level metaprogramming, I would say, just like pattern matching and rewrite rules. But later on, it was picked up in several projects like Lift and Elevate and to some extent EXO as well at MIT. So you can do that in better ways than we did at the time, like safer ways. But sometimes it's actually feasible to implement user schedulable languages as pragmas or as kind of directives using rewrite rules. But that made us think that there is something beyond. So we should probably, and that's what I'm just finally going to advertise for in terms of a vision for building domain-specific languages for expert programmers, for like performance experts. And I think the better inspiration here is what Kennedy's group coined like telescoping languages a while back. The idea is more to provide some hints for the compiler rather than trying to tell exactly the compiler what to do. So you want to build a compiler that will eventually learn how to do the work of experts, maybe using ML at some point. Not by putting all the intelligence in the scheduling language. You can do that, but so far our experience, and I think what I've learned from industry development in XLA, shows that this is a bit difficult to convince performance engineers to go that path, because it's learning yet another language. It's learning how to develop the DSL itself, because you typically don't have the one you want. Yes, you can make it easier using build it, but it's still like several steps before getting there. So if you could incrementally teach the compiler how to do things, it would probably be easier for like practitioners. And I think telescoping languages had it very well in a narrow spectrum. I think it was mostly for numerical libraries, but we had some similar idea a while back also, which is we call it split compilation, where you would annotate a bytecode language. In this case, it was either Java or Mono, like C#, with semantic annotations that would make like essentially convey static information or domain-specific information to a backend compiler, similar to telescoping abstractions in this case. The question is, how do you do that for real, for like modern problems, domain-specific accelerators in particular? And it remains a challenge to reconcile heuristics in compilers with domain information or control capabilities by experts. So I think I would advocate for this direction because I think it's easier to adopt, but I'm not saying I know how to do it. So that's where I'm really calling for help. One observation as well that I made earlier is that, I mean, I'm ashamed of saying that because I said the exact opposite when people were doing that 15 years ago, but sometimes you have to just relax correctness when you think about compilers, which is a very shocking thing to do, but you have to realize that some of these DSLs, they are used for a single program. It's like when you write a script, a shell script to sort your pictures from your vacation. You just don't care whether the regex is proven correct or anything. You just do it. It seems to do the work. You do the rewrite of all your pictures and you're done. And you just forget about the code. So I think some people do DSL programming exactly like this. So they actually don't want to write a full-fledged DSL frame, the domain-specific framework. They want to write something once that can be tweaked as long as the person is alive and understands their own code for a few months, and that's it. And it's not like very mature, robust software, very much unlike traditional compilers. So I think this is a nice opportunity because you can do unsound things. You can do ML, for example, but it's also very strange because maybe you're kind of breaking like it defeats the purpose of building a compiler in the first place. It's just a question. So controllable compiler optimizations, this is where we headed to. So it's like user schedulable languages, but at lower level. So instead of building a framework to build user schedulable languages, which makes complete sense, what we did is one level down in the IR itself, in this case in MLIR, which is a very extensible IR, you build enough capability so that you can write IR code that meta-programs itself in a way that will serve the purpose of implementing other domain-specific frameworks. So I don't have time to go into any detail. There have been lots of presentations on this. We also just published a paper that will be presented at CGO. But the idea is that hopefully with this approach, you don't have to put this, it's called the transform dialect, what's inside MLIR. You don't have to put the transform dialect in the hands of performance engineers. This is way too low level. But we can incrementally build a compiler with these principles that will be easier to adapt for domain-specific purposes along the way. I don't know if we'll get there, but that's what we came up with from this experience. So I'm skipping any of these details. Conclusion. So are there any kernels left behind? So yeah, initially I wanted to pop all the kernels because it's much better and doesn't break your teeth. But most likely that's not going to be feasible. So we have to live with those kernels that are not popped. And you can actually look around and try to learn why kernels don't pop when you do popcorn. There are all kinds of reasons. It's a very interesting chemistry lesson. But the lesson, I think, is compilers are not dead in this world. So the fact you have low-level programming interfaces like kernels doesn't mean the compilers should not play a role. In particular, if you can optimize together kernel code with automatically generated code, and if you can bridge the two by teaching compilers how to deal with those domain-specific abstractions, we would be much better off. I've sketched some directions, but I think now the floor is yours to solve the problem. Thank you.
Any questions? Mark.
It's not as much of a question as an observation of what you were saying about you write it once and then it does its job and then you throw it away. But what I've seen is that somehow it doesn't get thrown away. And you end up with incorrect results because it's used for something which you hadn't intended, quick and dirty sort of thing that still has a life of its own. So yes. I'm sure you've seen it too, but it's just an observation.
Yeah, even in monolithic designs. Yeah, that has my only hope is that by making things more modular, the part that should have been thrown away would be smaller. So maybe it's easier to do it. So there are less reasons to keep it around. But yes, it's a hard problem. It has been there forever.
So I have two questions. First, it looks like in machine learning, there's so many things we are rewriting, but for so few algorithms. You can just write a compiler for matrix multiply, compiler for something, compiler for the few algorithms, be done with it.
Yes, so that's what people did initially. I mean, if you look at XLA internals, they have so-called emitters, especially for TPUs, that those ones are not open source. There are basically two. So there is like two code generation templates, one for convolution in particular, because convolution was everything at the time. And then, I mean, in particular, a matrix product can be a convolution like 1, etc. So that was great, but I think now it's not enough. And I have a major disagreement with former colleagues like the MLIR design side who have exactly your vision, saying we have tons of architectures or different ways to specialize the code depending on the shapes and everything, but we have just one algorithm. I mean, if you look at attention, it's not quite true. And because attention doesn't scale, also there are lots of variants of attentions like tree shape, whatever decompositions that approximate attentions in different ways. There are also SSMs and all kinds of recurrent networks coming back. I would say that it's exaggerated to say that. So yes, there are very few kernels, very much unlike HPs, but still enough to make room for real compiler.
So other thing is, after listening to your talk, I don't know that you are very optimistic about compilers or very pessimistic.
I don't know myself. I don't know. I'm asking for help. I used to be optimistic.
Oh, you do, okay.
Well, since I think the tea breaks has arrived, let's continue the discussion over the tea break. But thanks again to help.